In this lesson, we're going to look at the stoichiometry of gases. We're going to combine the idea of density with the ideal gas law and look at Dalton's partial pressures, Dalton's law of partial pressures. We will also work a couple example problems. So first up, density is a characteristic property. You know what density is. It's mass divided by volume. Now, we've dealt with that in solids and liquids, which is easy because solids and liquids don't change their volume when we change their pressure, at least not appreciably. They don't change their volume when we alter their temperature, again, not appreciably. But gases, that definitely changes. If we change their temperature, their pressure, we can manipulate their volume. And so we have to include pressure and temperature when we are talking about the density of a gas, because if we change those things, it will alter the density of the gas. Generally, we'll report gas densities at STP. Sometimes you'll see NTP, normal temperature and pressure. That's 20 degrees Celsius as opposed to 0 degrees Celsius, but still 1 atmosphere of pressure. So here's all of this. Now the algebra on here is fairly straightforward. Density is mass divided by volume. The ideal gas law, remember, is PV equals nRT, but if you solve that for volume, then volume is nRT divided by pressure. And then if we sub that into the density equation, density is mass divided by volume. Remember, divide is invert and multiply, so we have density equals mass times the inverse of this, pressure times, pressure over nRT, which gets us MP divided by nRT. Now that M over N is the definition of molar mass. So we can replace that with the capital M for molar mass. That's grams per moles. Remember, that is the same as the atomic mass on the periodic table. It's grams per mole instead of atomic mass units. So this is just another expression for density. Density equals molar mass times pressure divided by gas constant R times temperature. And this lets us know the density of any gas at these pressures and temperatures. Now, because molar mass, capital M, is grams per mole, M over N. If I solve this for little n, or moles, moles is equal to mass divided by molar mass, and we can throw that into the ideal gas law, PV equals nRT. We make this substitution where N is really M over N, so we have pressure times volume equals grams per molar mass, grams per mole, times RT. And if we solve this for M, I'm just going to multiply both sides by molar mass and divide both sides by PV. We get molar mass is actually equal to mass times gas constant R times temperature divided by pressure times volume. So this is handy. If we know the mass of the gas and we know temperature, pressure, volume, we can use this equation, which is just a simplification of the ideal gas law and density, to find the molar mass of the gas, which could help us identify. We'll look at an example that does that. So, example, determining the density of a gas. What is the density of molecular nitrogen at STP? Well, remember, standard temperature and pressure, that's a pressure of 1 atmosphere, and that is a temperature of 0 degrees Celsius, but we don't want degrees Celsius. Always in the ideal gas law, temperature has to be measured in Kelvin, and so 273 Kelvin. And then the density of molecular nitrogen. Remember, nitrogen is one of the diatomic molecules. It's N2, and so nitrogen has a molar mass of 14, so N2, 28 grams per mole. This is our capital M for molar mass. That's actually a capital mu, but a capital mu and a capital M look exactly the same. So then we just use our equation to determine density. Density is M times P over RT. Now, we have to make a wise decision on R. Our molar mass is grams per mole. Our pressure is atmospheres. Our temperature is Kelvin. And we want our final unit here of density to be mass over volume. Our mass is going to come from grams. Our volume is going to come whatever volume we have in R, which is probably liters. So we're going to end up with grams per liter. And we want our atmospheres and our kelvins to cancel out. So what we're going to choose is R is 0.0821. We're going to use 0.8206 or 0.0821 liter atmospheres per mole Kelvin. Right? Now that mole cancels that mole, that Kelvin cancels that Kelvin, that atmosphere cancels that atmosphere, and we are going to be left with grams per liter. And so we can say this is equal to 28 grams per mole times the pressure of 1 atmosphere divided by R 0.0821 times T, which we found is 273. And if you work that all out, you get a density of 1.25 grams per liter. So the trick here is to pick the R that makes your units work. We had atmospheres and liters, so we end up canceling our atmospheres and having our unit of liters. Another example, determine the molecular formula of a gas, cyclopropane, given that it's 85.7% carbon and 14.3% hydrogen by mass. First, we got to find the empirical formula. So, been a while since we've done this, but remember, empirical formula is the most reduced form. And so, this is pretty easy. We just say, oh, well, let's assume we have 100 grams, so 85.7% carbon becomes 85.7 grams carbon, and then carbon has a molar mass of 12 grams per mole, or 1 mole per 12 grams. We might make that multiplication. 85.7 divided by 12 is 7.14 moles, and then we have 14.3 grams of hydrogen, molar mass of hydrogen, of course, 1, so 1 mole per 1 gram, and this gets us 14.3 moles hydrogen. And then we just need their whole number ratio, so 14.3 to 7.14 is close enough to 2 to 1 that our rounding errors are going to tell us it's 2 to 1. So that tells us the empirical formula of or cyclopropane is CH2. Now, that's not the molecular formula, that's just the formula in the most reduced form. So now we're going to be told find its molecular formula, given that 1.56 grams of cyclopropane occupies a volume of 1 liter at 0.984 atmospheres and 50 degrees Celsius. So now we can use that other formula. Molar mass is equal to mass times gas constant R times temperature divided by pressure times volume. Once we find the molar mass, we can combine that with the empirical formula to actually find the molecular formula. So 1.56 grams, and so then we have liters in atmospheres. So again, we're going to choose the gas constant that involves liters in atmospheres, 0.0821, and then of course the units on this are liters times atmospheres times mole or per mole times Kelvin, times temperature, 50 degrees Celsius. Remember, we want to change that to Kelvin, so 273 plus 50 is 323 Kelvin, and then we'll divide that by pressure. We have a pressure of 0.984 atmospheres times volume, and we have a volume of 1 liter. So this liter cancels that liter, this atmosphere cancels that atmosphere, this Kelvin cancels that Kelvin, and we will be left with grams per mole. And so if we work this math out, 1.56 times 0.0821 times 323 divided by 0.984, that is equal to 42 grams per mole. So this tells me every mole of cyclopropane has a mass of 42 grams. Furthermore, we know that the empirical formula is CH2. Well, CH2 has a molar mass of 12 plus 2, which equals 14 grams per mole. So if we take the molar mass of the thing, 42, divided by the empirical mass, 14, we see that the molecular formula has 3 times the mass as the empirical formula. So we just take CH2 times 3, and that gets us C3H6. So there is the molecular formula for cyclopropane.